But I'm gonna get started on the second part now. Okay. So I'm on slide 13 in your peer deck. I want you to do this slide before you start your simulation, okay? It says, what is this passage saying about molecular polarity? And I have the definition of it, electric charge in a molecule, okay? So as you're reading this paragraph, think about if it mentions charge in a molecule, um, there is going to be molecular polarity. Okay, be as detailed as possible by only using the passage. Okay, so if it talks about charge, it's also talking about molecular polarity. Okay, and if it's talking about polar molecules or non-polar molecules, it's talking about molecular polarity. All right, that word polar is inside polarity. Okay, after you do this slide, the next slide on your peer deck is the simulation slide and the instructions on there, okay? We're gonna adjust electronegativity to see what happens with electrostatic potential, okay? And I am gonna click this bottom link down here to open it up in a new window so you guys could see it better, right? I'm gonna get rid of these arrows, okay? And I'm gonna turn on electrostatic potential. Okay, so I click off bond dipole and I turn on electrostatic potential, right? Notice how you get this field around your molecule, right? And you get a bar above that that says electrostatic potential. This field around the molecule is a, a charge field. Okay, so charge is coming out of atom A and charge is coming out of atom B. Okay, you could also call this um, electrostatic field. Okay, you could also call this an electrostatic field. It's up to you what terminology you want to use your observations for. You could use a charge field, you could use electrostatic field. Okay? Now let's talk about the bar, okay? Notice how your field has a blue color for atom A. Blue means positive. It's a positive charge. Or the electrostatic potential is in the positive direction, okay? The darker the blue, the stronger the positive charge. So the furthest to the left has the darkest blue. So this is the strongest point in the bar, okay, that has the strongest positive charge. And as I move to the right, the blue color fades. That means the positive charge is getting weaker, okay, until eventually you hit this white space. There's no charge here. It's zero charge. The molecule is neutral, okay? There's no electrostatic potential. All right, there's three ways to interpret that white. Now we're going to talk about the charge coming out of atom B, okay? The charge coming out of atom B is red, okay? And it's a weak red because it's a faded red, okay? Red means negative, so this is a weak negative charge, okay? Or the electrostatic potential in the negative direction is low. Okay? It's up to you how you want to phrase that in your observations. Now, I'm going to talk about the extreme end of the negative charge or the negative electrostatic potential. Boom. This is the dark red, okay? That means it's a strong negative charge, okay? Strong negative charge. And as I move to the left, the red fades out. So the negative charge is becoming weaker, okay? Or you could say the electrostatic potential in the negative direction is becoming lower or smaller, okay? Until you get to the white spot again, which is zero, zero charge. There's no charge around the molecule. All right, so let's talk about the charge around the molecule again, or the electrostatic field or the charge field. This side has a weak positive charge, and this side on atom B has a weak negative charge. What made these charges? We have to look at the electronegativities between both atoms, okay? So the electronegativity of atom A is at zero electronegativity, okay? Or 0% electronegativity. Or atom A has no electronegativity. Or atom A is at the extreme end of the less point, the less section on the electronegativity scale. Okay? It's up to you how you want to interpret this blue tab. Okay? Now let's look at atom B's electronegativity. Atom B is at tick mark 5 or the halfway point on the electronegativity scale, or you could say it has 50% electronegativity. Okay? Now let's compare atom B's electronegativity with atom A's electronegativity. Atom B's electronegativity is stronger than atom A's by 5 ticks, okay? Or you could say it's 50% stronger, all right, than atom A's. And that what's okay, and that difference in electronegativity between atom A and atom B produces the difference in charge in this molecule, okay? It produces a weak negative charge on B and a weak positive charge on A, right? So I wonder if this 50% difference works all the time, okay? So let's check it out, right? So I increased the electronegativity of atom A, okay, by 5 tick marks. I also increased the electronegativity of atom B by 5 tick marks, okay? It's still 5 tick marks away from, they're still 5 tick marks away from each other. Or atom B still has 50% greater electronegativity than atom A, okay? Atom A is still weaker. And we still have the same situation, a weak negative end and a weak positive end, okay? Now I'm going to set this back up to its original position. So I'm going to move atoms A negativity to 0 or to the far end of less. And I'm going to move atom B's electronegativity to the halfway point. Okay. Now I'm going to increase atom B's electronegativity. Okay. I'm going to slowly increase it. Watch what happens to the charge field, the charges coming out of each atom. Look at the color. Okay, the color is getting darker. That means the charges on each end of the molecule is becoming they are becoming stronger. Okay. All right. Now atom B has full electronegativity or 100% electronegativity. Okay. While atom A still has zero or no electronegativity. All right. Atom B is 10 tick marks away from atoms atom A's electronegativities. Okay. The electronegativities of both atoms are at the extreme ends of each other. All right. Look what it produced here. It produced the deepest colored red and the deepest colored blue. All right. That means it's the strongest blue. The strongest positive charge that atom A can get. And that deep red means it's the strongest negative charge that atom B can get, right? So this molecule has the strongest of both charges on each side of it. Now I am going to decrease the electronegativity of atom B. Observe what happens, right? So as I'm making atom B's electronegativity weaker, I'm approaching the electronegativity of atom A, right? Notice how the color is getting fainter. That means the charges on each end are getting weaker until I have no charge, right? Remember, white means no charge, right? So now look at the electronegativities of both atoms. They are exactly the same. They are exactly the same, all right? You may wonder, when the electronegativities of each atom are equal to each other, are you always going to get no charge inside the molecule? All right, let's check it out. I'm going to move them both to 5, tick mark 5. They're equal again. All right, now I'm going to move them. Oh, observe, there's no charge inside the molecule. Now I'm going to make them equal again. There's no charge, there's no electrostatic potential inside the molecule, all right? So now, instead of giving atom A 0 electronegativity, I'm going to leave it at 100% electronegativity, but I am going to slowly decrease the electronegativity of atom B. All right? I'm slowly decreasing the electronegativity of atom B. Notice what's happening to the charges around the molecule. All right? So I'm creating a charge difference inside the molecule. One end has a positive, the other end has a negative, all right? And the charge is getting stronger the greater the difference of electronegativity between each atom, all right? Boom, all right? What's different than the first setup that we had? Well, now atom B is at 0 instead of atom A, okay? And atom A is at 100% electronegativity, right? That created a flip in color. Before, atom B had a positive, atom B had a red color around it. It had a negative charge around it when it had the higher electronegativity. But now atom B has a lower electronegativity than atom A, so it takes on the positive charge instead, right? Go ahead and write all your observations down, okay? Just tell me what you see. Don't try to interpret your observations, all right? So after you write down all your observations, look for patterns. As you're increasing or decreasing electronegativity, what's happening to the charges around the molecule, right? What's happening to the charge on B? Is it increasing in the positive direction or is it increasing in the negative direction, right? Look for trends. Compare electronegativities of both atoms. Compare electrostatic potentials of between both atoms, okay? Make a comparison chart after you write your observations. Compare and contrast. Put that in the chart, right? If you want to. It's up to you how you want to organize your observations after you make them, okay? So this is an opportunity for you to come up with your own ideas, to organize your own information that you gather from this simulation, all right? And that is an amazing and powerful experience when you use your own ideas, all right? So that is it for this demonstration, okay? There's still lesson 2 to complete, so go ahead and complete all the slides on lesson 2, and I will see you guys in the live session tomorrow, all right? I will post an assignment associated with this recording in the classwork section, all right? I hope you guys have a good and wonderful day. Sorry for the delay in this video, right? Have a beautiful day, everybody.